Yeah, wow, we only have this class and one more class besides the makeup exam. So I have a lot of topics I have to talk about. I'm going to try to talk a lot faster today. Um, Not really, but I don't know. We might, well, we'll see. Um, so what we have coming up is uh, makeup exam. Monday for the night class and Tuesday for the day class. And I'll just bring copies of every exam. So, when you get here, just let me know which one you want. And that's all we're doing in class. So if you don't want to take a makeup, just don't come. I would recommend, I don't know, but it might be sort of like, feels sort of nice to sit while everyone else is stressing out and just like sit during the exam and not have to worry about anything.
Can we do our makeup lab during the class time?
No, because I have to be in here.
You have to be in there for the makeup lab, it's not just.
Oh, the makeup lab. Well, that's a good question. If you're doing, anyone who's doing just one of those makeup lab worksheets, you can work on it during class, sure. For anybody who's staying for a makeup lab and hasn't taken the post test, remember we did that multiple choice pre-test, then I want those, but I guess they could do it during the test too. So yes, anybody could work on the lab during class time, I guess, if you're not taking a makeup. Just come talk to me before class and I'll get that all set up. Okay.
When is the post multiple choice test?
It's in lab this week. And then the final, exam 5, is Monday, December 16th at 6 p.m. for the night class, and Friday, December 20th at 2 p.m. for the day class. So you sort of, if you can make it to those 2 times, you have your choice of the first day of finals week or the last day. And the topics, well, I guess, so it didn't really occur to me how little class time we have left. So we'll see what we can get through, but we'll definitely have conservation of linear momentum and conservation of energy. And we'll definitely have rotational kinematics. We'll see how far we can get in rotational kinetics. Hopefully this too, but and then the last thing you have coming up for this class is the problem set. That you're just going to turn into me, and it's due by the last day of finals. So it's due by Friday, 12/20. And you can turn that in as a hard copy, bring it to your final or whatever. Or there's also a D2L Dropbox set up, so you can just scan it and submit a PDF to the Dropbox. But please don't email it. It's so easy for me to lose email, lose it on emails. It's a lot easier for me to keep track of it if you put it in the Dropbox. Okay. Any questions about the end of the semester? Okay. So last time I introduced the last equation for this topic. So I mentioned conservation of energy. And conservation of energy says take the potential energy plus the kinetic energy at one instant. That has to be equal to the potential energy plus the kinetic energy at a different instant. Okay, but this only holds under certain conditions, and so we have to be really careful about what these conditions are. This works really well for some kinds of problems, but you can't use this form for other kinds of problems. So for this to hold, the chosen object can't have any work done on it by non-conservative forces. Okay, so at first this looks like a big problem because no interesting problems, nothing the least bit useful has no non-conservative forces. Like any real problem has non-conservative forces acting on whatever object you're looking at. The only case where you wouldn't have that is free fall, pretty much. But this doesn't say that there can't be non-conservative forces. It just says whatever non-conservative forces there are can't do any work. So what kind of forces don't do any work? That's the next question. So what types of non-conservative forces do zero work? And zero work is done by any force that's perpendicular to the velocity vector at each instant. Okay, so basically at every instant, the direction of motion has to be perpendicular to the force. If that's true, then that force does zero work. So here are the two important examples, the two most important non-conservative forces that do zero work. The first one, and this is a really, this one is the most important. Any normal force does zero work. And so to think about why that is, think about an object without friction sliding along an incline. Then the forces acting are the weight force and the normal force. What's the direction of the velocity in a problem like this? Well, there are two possibilities, but what are the two possibilities? Yep, that's right. But it can slide down the ramp or up the ramp, right? and the force is perpendicular to the ramp. So this is a case where the velocity vector, no matter where it is along the incline, is perpendicular to the force. And so that does zero work. And that's a big deal because normal forces come up in tons of problems, right? The second case where a non-conservative force does zero work is any centripetal force during circular motion. Anyone know what song I was humming as I did that? Yeah, that's right. That's what I was trying to remember that video. I only did that because that's what it looked like when you were pointing both directions. So an example here is like if you have an object swinging around in a circle, okay, from a cable, a free body diagram, there's a tension force that way, a weight force this way. And that tension force is always pointed toward the center of that circle. It's always a centripetal force. And so that tension force does zero work. Okay? I guess if I had to think of, so the most important non-conservative force that does work, that, you know, you can't just assume the work is zero, is friction. So if there's ever friction in a problem, you can't use conservation of energy. You can use that original work energy principle, but we're not going to do problems like that, okay? So friction says you can't use this approach. But as long as it's made up of conservative forces, normal force, and centripetal forces, you can use conservation of energy. Okay, so let's do an example problem. And I'll just write this up to remind you. So conservative forces have potential energy. The potential energy for the weight force is equal to mgh, and the potential energy for a spring force is 1/2 k x squared. And those are the only forces that have potential energy. And conservation of energy says choose your two instants as long as there's no work done by non-conservative forces in that whole time interval. Potential energy at instant 1 plus kinetic energy at instant 1 is equal to potential energy at instant 2 plus kinetic energy at instant 2. Okay, so here's the example. So that's a ski hill. There's a skier at the top. And let's say that this ski hill is, let's say it's 40 meters high, okay? 40 meters change in height from the top to the bottom. And what, mathematically, how would you describe the shape of this hill? Like maybe there's, I don't know, like there's definitely like a negative, maybe a negative 0.5 x plus maybe like 20 times the sine of x squared plus probably a log or something. Okay, so let's say that that's the function that describes this hill, okay? I'm just writing this function out because, okay, I'm writing this function out because if we were going to solve this problem using Newton's laws, we would have to, at every instant, have a way to represent the direction of the normal force. We'd have to write that as a vector, calculate the acceleration at that point, and then we'd actually have to use calculus to integrate it. But then we could go through and figure out how fast he would be going at the bottom. That's what I'm going to do here. How fast at the bottom. But the really cool thing about these problems, this approach, is we, as long as we don't have any work done by non-conservative forces, nothing about what happens in the middle matters. All we have to know is stuff at the two endpoints in order to do this calculation. So for some problems, I just wrote this up here to point out how much simpler this is for some problems than using Newton's laws. Okay, like that, the shape of the hill is never going to come into it. Okay, so what are the two instants? We know that conservation of energy deals with two instants. What are the two instants we want to deal with? Yeah, it's just like it used to be with kinematics, based on where you know stuff and where you want to find stuff. Those are your two instants. So instant one is at the top, and instant two is at the bottom. And I'm just going to go through, calculate any potential energy at each instant, calculate the kinetic energy at each instant, and then we'll just plug it into that equation. Okay, so what kind of, well, it's probably not a bad idea to think of drawing like sort of a representative free body diagram. If you don't want to do this, when you use Newton's second law, I definitely want you to do it, but for this problem, these kind of problems, that's his hat. For these problems, if you don't want to do a free body diagram, that's fine, but there's a weight force, right? So 9.81 times the mass. What other forces are acting? Yeah, normal force. And we're going to assume no friction, because like I said, this approach doesn't work if you have friction. So potential energy is only gravitational. And it is m times 9.81 times h. And now in order to choose this h, we have to choose a zero height. Remember, that's arbitrary, but we have to be consistent through the problem. So what do you want to choose as your zero h? There's no wrong answer, but yeah, the bottom probably makes the calculation the simplest. So let's say h equals 0 here. So then what's h at the top? 40, yep. So you get 392.4 m. And then the kinetic energy, we're assuming that he's at rest at the top. So the kinetic energy is 1/2 times the mass times the speed squared. So that's 1/2 m times 0 squared, so 0. And then at the second instant, the gravitational potential energy is 9.81 m times the height. What's the height? 0, so this is 0. Kinetic energy, we can't calculate because we're trying to find that speed, so we'll just leave it as the variable v. So this is 1/2 m v squared. And now you just add up everything in the left column and set it equal to everything added together in the right column. So we have, for conservation of energy, 392.4. Do I have that right? Did I? Plus 0 is equal to 0 plus 1/2 mv squared. Oh, and I left off the m here. There's an m on this one. Okay. And now you have m's on both sides, so those m's cancel. And now you just do the algebra, multiply both sides by 2, and you get 784.8. Is equal to v squared. So what's v? 28.1. So v is plus or minus 28.01 meters per second. This is speed. It's always positive, so we want the positive one. So if you just slid down this hill without, swooshing back and forth at all, so there's no friction at the bottom of the hill, you'd be going 28 meters per second, or like 60 miles an hour. And I mean, doesn't that seem amazing, kind of, that it doesn't have anything to do with what happens on this hill in between? As long as there's no friction and the only non-conservative forces do 0 work. So he could even catch onto a cable and swing through a circular loop-de-loop and go back to the hill, and this would still be true at the bottom. Any questions about that? Okay, let's do one with a spring. So let's say that a mass hangs from a spring. Say the mass is 10 kilograms. And let's say the spring has a constant K of 100 newtons per meter. And let's say that the spring is compressed .08 meters from its resting length. And released. What's the speed of the mass when the spring is 0.05 meters longer than its resting length. Okay, so first we have to think about what's going to happen. So if the spring is compressed so that the mass starts up here and then it's released, the spring is going to go down until finally the spring is stretched enough to turn the motion around, and it'll go back up here, and then it'll just oscillate back and forth between those points. Okay. And so if this, so let's say that this is the spring's resting length. Then this is 0.08 shorter than the resting length. This is 0.08 longer than the resting length. And we want to know what's the speed when it's here at 0.05. Okay, so what forces are acting on this? There's a weight force of 98.1. And there's a force from the spring that actually changes directions as the thing goes, but I'll just draw it like this. I'll call that Fs, the force from the spring. So in this case, there are no non-conservative forces. There are only conservative forces. But this time we have to account for the potential energy of the spring and the potential energy of gravity. Okay, so for these kind of problems, there's a trick that'll make your lives a lot easier. If you choose your h equals 0 to be at the resting length, then you can use the same variable for, or the same number, the same value for h, for the gravitational potential energy, that you use for x, for the spring potential energy. So what do we want to use as instant 1? It's a know stuff, want stuff kind of thing. So let's say that this is when it's compressed 8 centimeters from the resting length. So the gravitational potential energy is 10 times 9.81. And what's h? H is 8 centimeters. Positive 8 centimeters because it's in the, it's up from, question? 8 centimeters is 0.08 meters, so I just said that. But I'll leave it as meters when I write it. And what do you get when you multiply those? 7.84. And what are the units of potential energy? Joules, yep. And now we have to deal with the spring potential energy. So that's 1/2 times the spring constant, 100, times x squared. We can use that h value as our x, because even though h can be positive or negative, in the spring equation, you're going to square it anyways. So that'll work out fine. So 0.08 goes in here. And you get a value of 0.32 joules.
Why is gravity not negative right now? But it's negative.
That's the force,
Oh,
but this is the potential energy. And then finally, we have to deal with the kinetic energy. What's the kinetic energy at this instant? Well, it's just released from that height. So if it's just released, it has no speed. So this is just going to be 0. And now at instant 2, the gravitational potential energy is 10 times 9.81 times, what's the height this time? Yeah, good. Negative 0.05, right? Because we're looking for 0.05 below the resting length. And that negative is important because you'll get different values for those two different locations. So you get negative 4.905 joules. Then for the spring potential energy, it's 1/2 times 100 times negative 0.05 squared. And you get a value of positive 0.125 joules. And now the kinetic energy is 1/2 times the mass times the speed squared, and we're trying to solve for that speed. So conservation of energy says 7.84 plus 0.32 plus 0 is equal to negative 4.905 plus 0.125 plus 5v squared. And if you solve this, you get v is equal to plus or minus 1.61 meters per second. It's a speed, so positive. There are two things. Well, first, any questions about that? So you just have to figure out what conservative forces, figure out what conservative forces are acting and, express the potential energy for each of those. Make sure the non-conservative forces aren't doing any work, but really they just won't be in these problems. Calculate the kinetic energy and then just solve conservation of energy. I want you to recognize something about these spring motions. So this gives us the speed. What's the velocity? What's the velocity vector of that thing, that mass, when it gets to that point? Okay, so that is correct. When the first time it goes down, it drops down and its velocity has a negative y value when it hits that point, right? But what about this point? Like, what says that we're calculating the speed at this point in the motion as opposed to the speed in this point of the motion? Because when it gets here, that would be a positive y velocity, right? Well, the answer is that those speeds would be the same, but the velocities would be opposite. So every time you get a speed of something connected to a spring, it corresponds to two different locations in that motion. Okay, one leaving and one coming back. Okay. Um,
Is that why it won't ever like reach back up to the highest point?
well, the way that we're treating this, it will reach back up to the highest point. It won't in reality because of heat losses and friction. Um, we can't deal with those with conservation of energy. Um, but this this calculation would work pretty well as long as you weren't planning on calculating the motion over a big amount of time. So yeah, according to this model, it goes forever without ever the amplitude of this motion ever decreasing. Um, okay, so yeah,
Question of your drawing,
yeah.
why doesn't the amplitude stop at 5 centimeters below resting point?
Why does it keep going
Yeah,
down?
it only goes 5 centimeters. Why did you draw it going down 8 centimeters?
Well, it's I just said we're going to calculate the speed when it gets to that point, but it keeps going, and it always, yeah, it always goes from, well, yeah. Any other questions? Are you are you laughing about my aborted explanation there? I think it doesn't
But the math works, right? Like if you put 0.08 to negative 0.08, you're gonna get like it has to go to 0.08 to make the math.
Actually, what I drew here, actually, I guess it's good that we are talking about this because now that I think about it, this is not right. If it was, so it's going to, what it would do is it would go way, way down, or depending on how stiff the spring is, maybe it wouldn't even go. Yeah, no, it's always going to go down farther than 0.08 because gravity's helping it go down, but it's not helping it go back up. So if you had a spring that was just, if you had a mass that was on wheels oscillating horizontally and you pushed it 8 centimeters past the resting and let it go, it would go from 8 centimeters to 8 centimeters on both sides. But there's an asymmetry because of the gravity, because gravity isn't symmetric the way spring force is. So yeah, it would actually, in this case, go down a lot farther. We could calculate where it would go. Want to do that? Come on, let's do it. You want to try to do it?
Yeah.
Okay. Yeah, why don't you take, oh, let me write these two things and then we'll, so two things I want you to notice about this. The first is, with springs, a calculated speed corresponds to two instants during the oscillation. I'll, just say coming and going. So opposite directions. And the second one, I know the second one was important. I'll be ready by the time she gets back. Dang, this is important. I know it is. So, oh yeah, when the spring, when a spring motion is vertical, the spring's resting length is not the length of the spring with the mass hanging. Um, it's the length of the spring. It's the length the spring would have lying, lying on a table or sitting in a box or whatever. Okay, so what that means is you take a spring that when you're holding it, it's 2 inches long or whatever, and then you hang a 10 kilogram mass from it. That 10 kilogram mass is going to stretch it down some, right? Now this spring is going to have a longer length. And which of those two are the important length? It's the one before you attach the mass to it. Do you know what I mean?
Is that the same, with gravity pulling on it?
Yeah, so before gravity's pulling on
Horizontal
it.
to measure an accurate resting length?
Yeah, right. It just can't be loaded at all. It's the length where the spring doesn't have any force on its two ends. Okay, so now the question is, how far below the resting length does the spring stretch before the mass starts going up again? So see if you can think through that one. It's a similar analysis to this.